Okay, great. I consent. Great. All right. Thank you all for having me here. Yeah, so I'm going to be talking about three-dimensional mirror symmetry, and I'm especially going to be focusing on some of the combinatorial implications of it with respect to one specific example, which is pretty simple, but it already has a lot of interesting stuff going on in it. So here's my plan for today. I want to start by talking about the enumerative geometry of quiver varieties and a little bit what sort of the general theory of that looks like. And then I want to give a rough schematic of what 3D mirror symmetry is and how it ties into enumerative geometry. And then, yeah, like I already mentioned, then I'm going to talk about one particular example and what it means combinatorially. So feel free to stop me at any time if there are questions. So to get us set up, let me introduce a little bit of terminology. So let's let X be a Nakajima quiver variety. And so what that is it's some sort of algebraic variety that we assign to some combinatorial data of a quiver and some numerical data. And Nakajima quiver varieties come equipped with the action of a torus. And so I'll use A to denote the torus that changes the framing. And I'll use C star H bar to denote the torus that scales the cotangent fibers. And I'm going to assume that the number of fixed points is finite. So I think in general, I'm not exactly sure how necessary this assumption is, but for everything I want to say, let's assume that the number of fixed points is finite. And so this is true for any type A or a cyclic type A quiver variety. Those are my main examples that I'm thinking of here. So roughly the object, that's the main object of study for me today is known as the vertex function. And what the vertex function is, well, roughly what you do is you pick a fixed point on your variety. And for each fixed point, you have a vertex function. And what it does is it's some sort of generating function that counts rational curves of a certain degree through that fixed point inside of the quiver variety. So more precisely, what you do to get the vertex function is you need to build some sort of good moduli space for the problem here of curves inside of the quiver variety. And the right one in this context is the moduli space of quasi-maps of a certain degree. And then what you do is you take a generating function for the equivariant Euler characteristic of the quasi-map moduli spaces. So I'm not going to say all the precise definitions about this, but if you sort of just want to think about it roughly, quasi-maps from P1 to the variety, well, they're basically maps, except they don't land in the variety always. Sometimes they land somewhere else, but most of the time they land in the variety. And there's a well-defined notion of degree of a quasi-map. In general, it's going to be a vector of degrees, not just a number. Or I guess the right way to say it is an element of the second homology. And I'll assume that infinity, so the curve passes through the point P. So it maps infinity into P inside the quiver variety. Okay, so I want to think about everything equivariantly with respect to the torus T that I mentioned earlier that acts on quiver varieties, and also with respect to the action of C star that acts by rotations on P1. And I'll denote coordinates on that torus by Q. And so very sort of concretely what you have with the vertex function is you have, okay, well, if you pick some basis for H2, then what you have is some generating function, and you've got a collection of Z variables, each to some power. And then you have some coefficients given by rational functions in terms of the equivariant parameters, A and H bar, and also Q. So you actually have to use equivariant localization to define the vertex function. because the quasi-map spaces are not, the evaluation maps are not proper. But let's not worry about that too much for now. The main point I want to emphasize that the vertex function is some sort of fairly explicit object, and if you apply equivariant localization, you can get fairly explicit formulas for it. Explicit in the sense of for any type A or cyclic type A quiver variety, you could program a computer to do it. So they're pretty explicit. So a priori, the vertex function is just a formal power series in the variables that count the degree. But it actually has a lot more structure than that. So a theorem of Andrei-Okounkov is that the vertex functions, if you normalize them correctly, then what you get is they actually give you a basis of solutions to a system of scalar Q difference equations. And so rather than just being a formal power series, they're actually, you could think of them as the Taylor expansion of some sort of holomorphic function. So the main reference for this is a collection of notes from Andrei-Okounkov. And so what exactly are the difference equations that they satisfy? Well, if you want to try to make it explicit and like write them down with formulas, it's a little bit challenging. But one way you could think of them is they're sort of like scalar versions of some sort of generalized QKZ equations that are constructed for quiver varieties. So just to provide an example, so we can have something very precise to think about, because I know I haven't said too many things very precisely yet. So if you look at maybe the simplest non-trivial example of a quiver variety, it's the cotangent bundle to P1, and it comes from this quiver data. So this variety has two fixed points on it. I'll call them P1 and P2. And the torus that acts on it is has 3 copies of C star. And I'm writing the coordinates subscripted. And in this case, the vertex function takes this form. So it's there's only one z parameter. And so it's the sum in one variable as the degree goes from 0 to infinity. And the coefficients of it are given by these rational functions, which are described by these Q Pachamar symbols. So you take 1 minus x, 1 minus q times x, and so forth. So this is some sort, if you look in the classic theory of like generalized Q hypergeometric functions, you can identify this one as some well-studied hypergeometric function. And in particular, this one is so this is for the first fixed point P1, and it's holomorphic near z equals 0. And if you look at the poles on this function, just from this term right here, at least in the A variables, poles occur when the ratio of A2 over A1 is equal to some negative integral power of Q. So if you want to get a better handle on how the poles and how the poles of the vertex functions work, the right object to use is the elliptic stable envelope. So I'm also not going to introduce a definition of this. The main reference for it is a paper of Okounkov and Aganagic, and they introduce it in order to study the monodromy of the Q difference equations satisfied by the vertex functions. And so what their main theorem says is that if you take the matrix of restrictions of the elliptic stable envelope, so okay, I didn't tell you what the elliptic stable envelope is, but you can think of it as some sections of line bundles over elliptic curves. So if you want to think about it very explicitly, you could have some collections of theta functions. And if you take the matrix of the elliptic stable envelope and you apply it to the vector of vertex functions, then what you get is you've actually canceled your poles in the A parameters, and you get something that's now holomorphic in the A variables. So the elliptic stable envelope is the object that takes our solution of our Q difference equation, holomorphic in one set of variables, and it switches it to solutions holomorphic in a different set of variables. So back to the example that I already showed. So before I showed you this vertex function, but now here I have the other one written down. You can see really the only difference between them is that the A parameters get flipped. And okay, I didn't write what these prefactors are, but there are some sort of factors that you have to have in order to get everything to work out correctly. And in this case, the matrix of restrictions of the elliptic stable envelope. So I've got 2 fixed points, so it's a 2x2 matrix. And there's all sorts of normalizations of the elliptic stable envelope, some of which are more convenient than others in various situations. And so my normalization for this particular example is given here. So you can see it's a matrix, and it's got entries that involve terms and theta functions, and then also other terms in our equivariant parameters. And so if you take, well, if I told you what C1 and C2 are, then you could work out an exercise and try to take the vector of vertex functions, multiply it by this, and try to see how the poles cancel. So we have this function that we obtain for each fixed point when we take the vertex function and we apply the elliptic stable envelope. And it's no longer holomorphic in the z variables. Now it's holomorphic in the a variables. And so a natural question to ask is, well, what sort of meaning does this function have? Is it just some solution of a Q difference equation, or does it have some sort of geometric meaning? And so to tell you the answer, or the conjectured answer about that, I need to tell you about what 3D mirror symmetry is. So in general, what 3D mirror symmetry says is that for a given variety with a certain collection of decorations on it, there exists another variety so that the two varieties' geometry is intertwined in deep but non-trivial ways. So more specifically, what we have is between a variety and its 3D mirror dual, which I'll write using the exclamation point, we should have, first of all, a bijection on fixed points. So, well, that makes sense if we want to identify this function as something related to the geometry of the dual variety, then I should have a bijection on fixed points because, well, that's how many of these I'll have. And then also what we need with 3D mirror symmetry is a way of interchanging the parameters for each of these varieties. So maybe for now we should think of these as Nakajima quiver varieties, although in general that won't be quite broad enough. But so when we apply the elliptic stable envelope to the vertex functions, we obtain something that's holomorphic in the a variables. And so if I want to identify that, for instance, as the vertex function of another variety, then those a variables should actually be the z variables on the other variety. So I need to switch them this way in order for this equation to work out. And this equation I like to refer to as 3D mirror symmetry of vertex functions. So roughly it says that the elliptic stable envelope is the object that transitions between the vertex functions of a variety and the vertex functions of its dual variety. So in general, to get the dual variety from a given, say, quiver variety, so I mentioned that you generally, it's not quite good enough to stay in the world of quiver varieties. Maybe that's not really my focus for today, but if you're interested in it, people are thinking that the world of bow varieties is the right place to study 3D mirror symmetry. Because in some sense, people expect it to be closed under this 3D mirror duality. Okay, so what examples have been studied so far about 3D mirror symmetry? So Ramani and his collaborators have studied a couple of these. And so, okay, so I referred to the equation on the last slide as 3D mirror symmetry of vertex functions, but there's also an analogous statement that just involves the elliptic stable envelopes. And so it's been proven for the cotangent bundle to the Grassmannian and its dual. So people have constructed the dual and then proven that the elliptic stable envelope has the expected 3D mirror symmetry relation. And it's also been proven for T star of the flag variety in type A, which is a quiver variety, but it's also been proven by Ramani and Weber for all types. It's also been studied for hypertoric varieties by Smirnov and Zhu, and they have proven it for the elliptic stable envelope and then also the statement for vertex functions. And my own research is focused on studying the vertex functions and trying to consider this 3D mirror symmetry expectation for particular types of examples. So particularly, I've looked at the vertex functions of the cotangent bundle of the Grassmannian, and also for the cotangent bundle of the full flag variety in type A. So I'm going to zoom in on this specific example today, and it has some interesting connections with Macdonald polynomials. So let's get into that.
So I have a quick question before we go. On the previous slide with the equation, the bottom equation, right? Is it clear that this is kind of a reversible process, that if one is the mirror of the other is the mirror of one?
Right. Well, that's a good question. So I said there's a 3D mirror statement for elliptic stable envelopes as well. And so if you know that statement too, then it is true. Because, well, basically what that statement says is that the elliptic stable envelopes coincide when you change parameters in the right way, and maybe after inversing or transposing or something like that. So if you know both statements, then it is the case that this process is reversible. You can apply the stable envelopes of the other variety to get back to what you started with. That's a good question though, because in general, it's, right, you could ask like, well, maybe this statement right here is strong enough that this already is strong enough. And I don't know, it's not totally clear to me if it is or if it isn't. For the cotangent bundle of the full flag variety, it is strong enough, but that's also a really nice space. So
I see. Thank you.
Yeah. Okay, so specifically, so I want to zoom into this cotangent bundle of the Grassmannian example. And even more specifically, I want to zoom into just one particular fixed point. So it's a known property that if you look at the matrix of restrictions of the elliptic stable envelope, that it gives you a triangular matrix with respect to some ordering on your fixed points. And so we should expect something particularly simple to happen if we look at the last fixed point with respect to that ordering. I will have an equation that looks like this. It's only got one vertex function instead of a sum of many of them. Now, in general, this equation is already very non-trivial. If you take some basic examples that people expect to be 3D mirror dual pairs, then this has already involved some pretty complicated combinatorics of expanding power series in various regions and trying to collect your terms in clever ways. So with that in mind, let's look at the example of the cotangent bundle to the Grassmannian. So this was considered by Ramani and his collaborators from the perspective of elliptic stable envelopes. And that's actually an assumption that we need to make, that n is at least 2k. If that's not the case, then the dual variety actually can't be constructed as a quiver variety, but rather you have to look at bow varieties in order to study it. So just to save on exclamation points throughout the rest of this presentation, I'm gonna call the dual T-star Grassmannian, and then I'm gonna call X the variety on the other side. And over on the left side, we have in A parameters because we have in framings, and then we have H bar, and then we have one Z variable, and that's because the rank of the Picard group over here is generated by the tautological line bundle. So you just get one Z variable. Or maybe more combinatorially, we have one vertex, so we get one Z. On the dual side, or on the side of X, we have two framings, so I get two A parameters. And then maybe I should write how many. So we've got K appears n minus 2K plus 1 times. So if you add it up, we're going to have n minus 1 Z variables, and then we also have H bar. And the change of parameters is given here. So, okay, well, we have in A variables and n minus 1 Z variables. So actually the right way to interchange them is going to be to interchange them with ratios of A going to Z. And then Z goes to the ratio of A. And then H bar gets swapped with Q over H bar on the other side. Now this change of parameters is not unique. It just depends on a lot of normalizations. Sometimes you might have other factors of H bar, or sometimes you may not have Q, or maybe you'll have more Qs. Okay, so we've got these two varieties that we think are going to be 3D mirror dual pairs. And we have some way of interchanging the equivariant and the Z parameters. So I also need to tell you what the bijection on fixed points is. And so fixed points on T-star Grassmannian are indexed by size K subsets of the set 1 to n. And fixed points on the variety X are indexed by pairs of based partitions that respect the dimensions. So let me say what I mean by that in a particular example. So if n is 7 and k is 3, this is the quiver data that we have. And what we think of is, well, each framing generates us some sort of partition, and we think about the partitions as being tilted up on their side. And so we'll get two partitions because we have two framings, and the condition that we need is that the total number of boxes above any given vertex is equal to the dimension on the vertex. So for instance, if we look at this vertex here with 2 on it, I need to have 2 boxes above it, and I get 1 blue box here, and I get 1 green box. Okay, or maybe if we check this one, this should be 3. So I get 2 green boxes and then 1 blue box. So in general, all such configurations of partitions that respect all the dimensions are going to be, that's how fixed points are indexed on this variety. So how do we get from a configuration like this to a fixed point on T-star Grassmannian? Well, what we do is we take the two partitions and we piece them together into a rectangle like this. And then we look, and there's going to be some sort of separating line that divides the partitions. And I just need to record the data of whenever I move downward. So I move downward at the 2nd position, the 5th, and the 6th. So my subset of 1 to 7 that I get in this example is 2, 5, 6. Okay, so we have our way of interchanging our parameters, and we have our bijection on fixed points. So I said I wanted to restrict my attention to the last fixed point. So here it looks like this. So I didn't tell you what the ordering on fixed points is, but the last fixed point in the ordering that I want to think about is when all the boxes are generated by just one partition and the other partition is empty. Or on the other side, it's the subset consisting of the last numbers between 1 and n. Okay, so I mentioned earlier that if you use localization, you can write some fairly explicit formulas for the vertex function. And so I don't want to write those exactly, but you can interpret them as being contour integrals. So this is written down in the work of Akankov and Aganagic in a different paper than the elliptic stable envelope one. I think it's called like Bethe eigenvectors, something like that. And so we interpret it as an integral, and we get terms in our integrals coming from the different arrows inside of the variety or inside of the quiver data. So I'm going to think about splitting up my integrand as some function, and then the contribution from the framing error that's shown in red is given by this product. So this is the Q Pachymer symbol, and then the infinity means that it's an infinite product. So you go 1 minus something, 1 minus Q times that, and then so on. So the reason why I want to think about my vertex function as being split up in this way is that when we do this, it turns out the integrand, the piece that doesn't come from the right framing, F, is actually the integrand that appears when we consider the vertex function of a different variety. Okay, so this maybe shouldn't be super surprising, right? I have some contribution from the red arrow, and then if I remove the red arrow, then I lose that contribution. Now, why would somebody want to think about it this way? Well, this variety, the quiver variety that comes from this data here, is a very simple quiver variety. Geometrically, it's actually just a point. So it's very simple. So maybe, well, are the vertex functions just trivial then, or what happens? Well, the vertex functions are, due to the definition of the quasi-map moduli spaces, the vertex functions actually remember some data about the prequotient. So this thing's a point, but it's a point that's obtained in a funny way. You have some big space and then you quotient it, and it just happens that what you get is a point. But the vertex function will remember, at least to some degree, what you had before you quotiented. So we have some non-trivial vertex function for this variety. So I'll call that one V lambda, and I'll just call the other one V of Z. Okay, so the advantage of thinking about it this way is that we can end up interpreting the vertex function of the dual of T star Grassmannian as a descendant insertion into the vertex function for this simple point variety. So how exactly does it work? Well, this product here that came from the red framing arrow can be expanded in terms of Macdonald polynomials. So this is something well known. I think it's in McDonald's book somewhere. So you can expand it in Macdonald polynomials. And so I can think about my vertex function as being the integral of something that involves Macdonald polynomials. And it's a theorem of myself and Andrei Smirnov that you can express descendant insertions into a point quiver variety through the action of Q difference operators. So I'm inserting here some infinite sum of Macdonald polynomials. So I should be able to express this in terms of some infinite sum of Q difference operators. So what exactly do the Q difference operators look like in this case? Well, in order to pinpoint them exactly, what you need to do is you need to look over to the other side and compare back to T star Grassmannian. So when you look back to T star Grassmannian and you use some sort of explicit formulas that have been obtained by myself and Andrei Smirnov for these point quiver variety vertex functions. So when you use both of these facts and make a wish list of what kind of difference operator it's going to have to be, it turns out that what's going to have to be the case if everything is not broken so far is that the difference operator that expresses this descendant insertion of a Macdonald polynomial is given by this right here. So what it is, it's, okay, so you have 1 for each natural number d, and you take some sum over integers that sum to d. And then you have some ratio of Q-Pachammer symbols, lots of numerators, lots of denominators. And then you have some shifts that shift the variables, which I'm calling x by q. So, okay, so none of this is like a theorem. This is, well, okay, the theorem was on the last slide. That was a theorem. But this is more of just like a wish list. We write down what we hope could happen in an ideal world if this 3D mirror symmetry is going to work out. And this is the family of difference operators that we stumble upon. So now if you continue looking at the combinatorics a little bit further, and if you dive into what exactly this function f looks like, then you can write down some other sort of condition that tells you, what it means in order for this to be the case. So given the form of f, this equation can be rewritten in different ways. And specifically, the way that you can rewrite it is you can actually deduce that what must happen for 3D mirror symmetry to work is that this family of difference operators needs to act diagonally on Macdonald polynomials with some known eigenvalues. So if you're familiar with the classical Macdonald difference operators, they're generally going to look much simpler than these. There are only finitely many of them, and they have much fewer numerators and much fewer denominators. So it's not at all obvious that this family of difference operators is even going to map polynomials to polynomials. A priori, it could map polynomials to rational functions. And it's also not at all obvious that these are going to commute and have Macdonald polynomials as their eigenvectors. Okay, so this is our wish list of what we were trying to do. If we wrote down the ideal situation of what should happen if this 3D mirror symmetry works out. And so now the question is, well, is it actually true? Does this family of difference operators really commute? Do they really act diagonally on Macdonald polynomials? And you can actually, you can prove it using fairly standard techniques. Numi and Shiraishi. Oops, I'm not sure what just happened. Does anybody have any questions while I'm scrolling back?
I'm just excited you brought up Noemi and Shirley because I was going to ask, that formula looks really similar.
yeah, right. Their formula is very similar. I mean, it's a little bit different, but basically, if you start with their formula, you can work with it a little bit and reduce to these. So they studied some family of operator. They've had a paper in circulation since 2012. That's cited in many places, but it was just posted on the archive last December. So if you study normal tech, use standard techniques to study these families of difference operators, you can prove that they behave as we expect, and thus also that the 3D mirror symmetry of vertex functions for this very specific variety on this very specific fixed point does what it's supposed to do. Okay. So just to summarize, we start with a very simple quiver variety, and we look at its dual, which is cooked up by some other means. And we do some reasoning about what would happen if 3D mirror symmetry of vertex functions was true. And what we end up discovering is some sort of new combinatorics of Macdonald polynomials, some new family of difference operators that characterizes them. So there are a couple, there's maybe one big glaring question about this perspective, and it's sort of like which one should we think of as coming first? And the way I talked about it today, we sort of start with this mirror symmetry of vertex functions, and we end up reducing it to some sort of combinatorial result, and then we scour combinatorial literature and we find the result, and then we deduce that mirror symmetry of vertex functions is the case in this example. So in general, I mean, you could hope that as 3D mirror symmetry is better understood, that methods could be developed that will, allow us to sort of reverse this perspective. Be able to take mirror symmetry, have some general statement about what it does, and then to be able to take that and reduce it and actually obtain theorems rather than just obtain conjectures that you have to prove some other way. Okay, so that's actually all I wanted to talk about. So it looks like we're done a little bit early, but yeah.
Awesome. Okay. So if we could give him a virtual Zoom round of applause. Or, I mean, I'll do a real one because I'm unmuted and live here, but great.